Hello, and thank you for your interest in the latest silicon carbide MOSFET from ROHM Semiconductor. In this short video, we will introduce the rapidly growing application spaces for silicon carbide power semiconductors, ROHM's technology development history, and latest status with Gen 4 trench MOSFET technology. We will also present new package options for improved efficiency and compact system design, and see how silicon carbide power devices can create system value for electric vehicles and industrial power systems. Silicon carbide is a wide bandgap semiconductor with 10 times higher breakdown electric field than silicon, making it an ideal material for high-voltage power switching devices. Silicon carbide power devices have been under extensive research in the past 30 years. And now the technology is delivering the promise of superior performance and making a big impact on power electronics design. For power converters requiring switching devices rated at 600 volt or higher breakdown voltages, silicon carbide MOSFET and diode often present ideal solutions to help improve energy efficiency, increase switching frequency, and make higher power rating possible. A growing list of industry segments are driving silicon carbide market expansion today. The solar inverters and energy storage systems, where increased efficiency could really help the energy harvesting. Companies running large-scale data centers try to minimize the energy waste and achieve their target power usage effectiveness. And one of the largest markets for silicon carbide, electric vehicle drive systems, where higher inverter efficiency means significant savings in the high-voltage battery pack. Thanks to the diversity of application spaces, silicon carbide market is expanding rapidly, and that is a key enabler of lower device costs for every customer. In the area of silicon carbide-based power devices, ROHM has been a leader of technology development and product commercialization in the past 20 years. Since 2009, we have integrated one of the world's leading silicon carbide substrate suppliers into ROHM Group companies. SiCrystal, based in Nuremberg, Germany, now provides high-quality materials for our silicon carbide device production, as well as for other device manufacturers. After several successful launches of silicon carbide diodes, MOSFETs, and module products, we now offer a diverse portfolio of silicon carbide power semiconductors. ROHM has established 6-inch silicon carbide wafer process to secure the capacity for large volume production. This allows us to fully support the automotive and industrial customers. In the coming months, we will release the 4th generation silicon carbide MOSFET products, which is the latest breakthrough in our silicon carbide technology. ROHM's silicon carbide MOSFET has evolved through a few generations, from the early planar gate design to the unique double trench structure offering much better performance. With chip design and process advances, from the 2nd generation to the 3rd, we were able to reduce the MOSFET specific on-state resistance by 50%. This means at the same die size, you will get much lower resistance during the conduction state and much lower energy losses. On the other hand, in most cases, you can use a smaller chip to handle the same power requirement, and that helps you reduce the cost. Our 3rd generation silicon carbide trench MOSFET is currently in mass production, and for the 4th generation, we will further optimize the trench design and bring down the on-state resistance value by another 40%. The design concepts of silicon carbide planar and trench MOSFET show our progress towards an advanced trench gate structure, delivering lower conduction and switching losses, robust short-circuit ruggedness, and flexible die attach methods. ROHM's 3rd generation silicon carbide MOSFET has a unique double trench design where the source-connected trenches provide electrical shielding for the gate region, reducing the electric field intensity and ensuring gate oxide reliability. The 4th generation device continues to be based on the principles of double trench technology. Furthermore, reduced cell pitch and thinner silicon carbide substrate are part of the new approaches to lower on-state resistance. A modified cell structure also includes measures to suppress short-circuit current level and reduce the capacitance between the gate and drain. For applications where high performance and reliability at the die attach interface is required, we will be offering metallization options suitable for silver sintering and soldering. With chip-level improvements designed in, the static and switching performance of Gen 4 MOSFET is significantly better than the current products. This is the forward conduction test data. With a chip size of 5 by 5 mm, a very low resistance of 12 mΩ is reached, giving it a higher current handling capability than the Gen 3 MOSFET of similar die size. With lower on-state resistance, better efficiency and lower cost can be expected. In this new generation products, it is also possible to drive the MOSFET with 15-volt gate voltage, like common silicon IGBTs. The right side figure shows dependence of MOSFET resistance on the gate voltage. For Gen 4 devices, the resistance increase due to 15-volt gate drive is very small. This could make it easier to replace the silicon device with silicon carbide and drive it at the same gate voltage levels. Normally, when we improve on-state performance of the MOSFET, the saturation current at high voltage will also increase. As a result, a compromise in short-circuit withstand time will be expected. This will not be the case for our Gen 4 design. In this device concept, a new cell structure helps suppress the short-circuit current while on-state resistance is being reduced. This design ensures safe turn-off of the power device during a short-circuit event. In addition to the improvement in conduction loss and short-circuit withstanding capability, we performed double pulse tests to analyze the switching loss performance. The devices are packaged into half-bridge power modules and compared side by side for 600-volt 136 amp switching condition. No external freewheeling diodes are used, and the gate drive voltages are the same values for Gen 3 and Gen 4 devices. This slide summarizes the faster switching speed and lower losses for the Gen 4 device. When the DIDT speed is the same for Gen 3 and Gen 4 parts, the lower Miller capacitance leads to faster DVDT transition time and lower switching energies for the new MOSFET. Approximately 50% reduction of switching loss has been confirmed without an increase in surge voltages induced by LDIDT. The reverse recovery loss is also lower for the 4th-gen MOSFET, especially at higher switching speed. This improvement is the result of a lower capacitance ratio between CRSS, which is the Miller capacitance, and CISS, the input capacitance. The optimized device capacitance helps suppress parasitic device turn-on during fast switching conditions and avoid shoot-through losses. Because of the significant reduction of total switching losses by chip design, high-frequency operation can be supported by Gen 4 MOSFET, enabling smaller power systems. To optimize the switching performance on discrete products, we are introducing new packages to enable faster switching speed and less losses. Our traditional TO247 package uses one source pin for both power circuit and the gate drive connection. This makes the source straight inductance part of the gate drive loop. When the load current rises and drops rapidly, a voltage is created by LDIDT, which partially cancels out the voltage applied by the gate drive circuit and results in slower switching speed. With the new 4-pin TO247 and 7-pin TO263 packages, additional driver source connections are provided, and the gate drive loop bypasses the straight inductance of the main current path, so it can make effective control of the MOSFET switching speed. The benefit of the new discrete packages is clearly shown in the switching waveforms. Using the same silicon carbide chip but different package styles, we are seeing a reduction of over 30% in switching losses by adding the separate Kelvin source connection, which can really help high-frequency operation with very little cost differences. The new discrete packages with Kelvin source connection are now available with the 3rd generation silicon carbide MOSFET. These packages will also be offered with the upcoming Gen 4 MOSFET. For some applications where a smaller system size is important, we will be offering an alternative solution to the discrete building blocks. The SDIP package, which is a versatile platform to integrate several power devices in one module, is available now as design samples. We can put a full bridge or a three-phase bridge inside the SDIP package, and this can make the circuit board much smaller than using multiple discrete devices. And for power converters of 10 or 20 kilowatt power level, such as EV onboard chargers, the SDIP package can also be a more compact solution than traditional power modules for lower cost. These modules will include insulation on the backside by ceramic material, where the heatsink can be attached. Among various applications of silicon carbide, the EV traction drive is a good example of value creation by the superior efficiency of silicon carbide power MOSFET. Conventional EV inverters are powered by silicon IGBTs and PIN diodes. The cost of these silicon devices is competitive, and their performance at full load current is excellent. However, the vehicle rarely operates at full load. When the inverter is working at partial load current, the knee voltage of silicon bipolar devices will hurt the conduction efficiency. On the other hand, the slower switching speed caused by IGBT tail current and the diode reverse recovery will also limit the switching performance in the conventional solution. To overcome silicon's performance limits, silicon carbide is the best candidate to lower inverter energy losses. With linear forward conduction characteristics and fast switching speed, silicon carbide can improve inverter efficiency by 3 to 8%, depending on the drive cycle. If we translate the energy savings into battery capacity and cost reduction, we can see how the more expensive power devices can lead to cheaper and better power systems. Another application where silicon carbide can help reduce system size is the onboard chargers for electric vehicles. There are different topologies available for the charger design. It can be unidirectional or bidirectional. And silicon carbide can be used for both the PFC section and the DC-DC converter stage. For example, the totem pole PFC circuit is a common place for silicon carbide MOSFET to contribute to a more compact system design. The topology eliminates inefficient diode bridges and utilizes power transistors in high-frequency, hard switching conditions. The transistor also needs a superior body diodes with low reverse recovery losses. Silicon superjunction MOSFET is not fast enough, so silicon carbide MOSFET becomes a preferred candidate. The body diode of silicon carbide has very little storage carriers inside the drift layer and switches nearly as fast as the Schottky barrier diodes, making it ideal for the totem pole PFC stage. With higher switching frequency and a smaller inductor, the onboard charger can be made smaller. In addition to these EV applications, other industries like the IT infrastructure can also benefit from the silicon carbide power technology. Data centers are big energy consumers growing at a rate that challenges the global energy supply. To mitigate this problem, governments have issued tightening guidelines for data center power usage effectiveness. The UPS system that data centers use converts electricity 2 times before reaching the IT equipment, no matter there is or there's not an electrical interruption. This ensures the most consistent power delivery to the servers, but it does waste energy and generate heat in the conversion process. With silicon carbide, we can substantially cut the energy waste of the UPS, especially in light load conditions, improving the data center's power usage effectiveness and reducing the cooling burden, besides the possibility to also downsize the power supply system. To conclude this short presentation, silicon carbide is clearly becoming attractive and competitive in automotive and industrial applications due to the efficiency improvement and other benefit it brings to the system, which can often outweigh the additional chip cost. ROHM is expecting to release our 4th generation silicon carbide MOSFET in the next few months, with industry-leading performance and robust short-circuit withstanding capability. We also offer a strong portfolio of discrete products and power modules to provide an optimal combination of efficiency, compactness, and value. Thank you for watching this presentation.